Hello. Good afternoon. Shall we start the session? Can you able to see this window? Can anyone respond, please? Can you see this B plus tree indexing slide? Hello. Can you see this PPT? Let me recall what is the previous discussion. So earlier we studied B tree indexing, right? The previous class, the discussion was about B tree indexing. Before that, I should make you understand why we are using this concept of B as well as B tree in indexing. Clear? You know, B tree is a data structure, right? B tree is a data structure. It knows some mechanism to store the data. So we are making use of this data structure to perform this indexing in database systems. That is the idea why we are going for this B tree as well as B plus tree indexing. Here, fine. And again, last class we know about the properties of B tree. We know that it is a balanced search tree. You know what is meant by a balanced search tree? It means we can say a tree is balanced if it has the ability to automatically adjust itself in case of any type of insertion, updations or deletions. So if the tree possesses this property, then we can call it as what? A balanced search tree. So both this B tree as well as B plus tree comes under the concept of what? Balanced search tree. Fine. Then let us understand why we need indexing. Clear? Say for example, you can understand why we need why the indexing is more important. Say for example, you are having a record note, right? You can consider it as some 1,000 pages note you having, right? And if you are interested in accessing a particular exercise, say for example, imagine you have a record note. The record note has around 1,000 pages and it has some 100 number of experiments. Clear? So if you want to access a particular experiment without any index, it will take so much of time. So imagine you have a record note. Even you can imagine our record note what we use in college. In the front side you will have exercise number followed by the title of experiment and followed by index or page number, right? Here the page number field or page number attribute plays the role of index, right? So imagine if you don't follow any index, what will be the situation? You are interested in searching some 100th experiment. Out of some 500 experiments, you are trying to search out some 100th experiment. What will be the situation if you don't follow any index? You will keep on flipping the pages one by one until it reaches a particular exercise of your interest. It will consume so much of time. Can you imagine? So the same thing, if you are following with a particular index, at the logarithmic time of 1, in the order of 1 itself, you can directly move to that particular record. If you're properly maintaining an index in the front page, at a single search, you can quickly go to the particular page or particular experiment without any much complexity. So that is the interesting part of this indexing. That's what we are preferring indexing in a large databases. Only with an efficient indexing mechanism, it will help us to retrieve the records of our interest. Clear? Next. So today we are going to see about B plus tree indexing. So again, this is also very similar to B tree indexing, plus some advantages over the B tree. And again, we know the basic idea of B plus tree also. It is also one of the binary set or balanced search tree. This also comes into the category of balanced search tree. Now the lesson outcome will be to understand the concept of indexing, to learn about B plus tree concepts, and to learn how records are physically stored and retrieved from a database. Fine. So let me go with the description of a B plus tree. So again, we know a B plus tree is a balanced binary search tree. Now you should have got an idea about what is meant by a balanced search tree. It means if a search tree or binary search tree has the ability to automatically adjust itself in case of any insertion, updation or deletion, then we can call it as a balanced search tree. That's why we are using the term balanced search tree. Clear? So that's what we call it as balanced search tree. And again, there is another one we call it as we can come across another term. It follows a multi-level index format. So what is mean by a multi-level index format? Say for example, imagine a situation, you have some 1 lakh records, right? You have your database which has 1 lakh records. Is it possible to maintain all those 1 lakh records into the main memory? What will be the situation? It will consume so much of memory. It will take so much of time for each and every storage as well as retrieval. So what this, you should imagine the situation like we won't store these records completely into the main memory. Instead, we will create so much of indexing based on this type of algorithms like B and B plus B, out of which we will get some intelligent mechanism with the index, and that index alone will be stored in the main memory, whereas the remaining records will be stored in secondary memories or in any other disk, secondary devices or a disk, right? That's what we call it as, that is a major understanding of indexing. So what is meant by a multi-level indexing? It means, say for example, you can imagine a situation, some person is coming to our campus. Here, some person is coming to our campus. He wants to know about the performance of a student. Or you can imagine some parents is coming to our college. He wants to know about the academic performance of a particular student. Fine. And say for example, who is he? Nirvikal, are you there? Nirvikal? Hello? You can unmute and answer. Are you there? Reshma, are you there? You can unmute and answer. Fine, I will take example as Nirvikal, right? So, if a parent is coming, Nirvikal's parent is coming to get the detail of his academic performance, what will be the flow or how he will access to our department? You can imagine the situation. First, his parents will inquire with the security officer about his department's building and all, and then he will come to office, right? In that office, he will inquire where is the security office. He will ask where is the college. We may have so much of colleges like Polytechnic, Teacher Education, and ACET. So security will direct him to ACET. So once he comes to ACET, he will go and approach office room, and his parent will get the idea where is the department. Then he will come to the department, and once he come to the department, he can able to access all the details of that particular person. This way we can imagine this here example for a multi-level indexing. So the security office will act as a one type of index, followed by the office will become another set of index, and finally the department, CSE department, will become the another index, and finally the academic record of each and every details, we call it as individual physical records of the particular student, say Nirvikal's record, right? That's what we call it as multi-level indexing. So this B tree allows this multi-level indexing format. And in the B plus tree, the leaf nodes denote actual data pointers. You know what is mean by leaf nodes, right? So a leaf node is nothing but in a tree, some hierarchies of a tree. It will in the topmost tree, we call it a topmost node, we call it as root node, and the intermediate nodes, we call it as internal nodes, and the last level nodes with no further children, we call it as leaf nodes. So here in the B plus tree, the leaf node denotes the actual data pointers. It means every records will be available with the leaf nodes. All the records will be available with the leaf nodes. Then B plus tree ensures that all leaf nodes remain at the same height. That is also one of the another description of B plus tree. If you're considering a B plus tree, the last level, or if you consider the leaf level, every leaf of the tree will be at the same level. There will not be any ups and downs. Finally, the last leaf nodes will be of the same height. Then another interesting thing is in the B plus tree, the leaf nodes are linked using a linked list. Fine. Therefore, a B tree can support random access as well as sequential access. That is the beauty of B plus tree. It will help to provide both random access as well as sequential access. Fine. Then the characteristics of B plus tree. Again, we can know the data records are only stored in the leaves. That's the thing we have we studied earlier. The leaves will consist of only the data records, and the internal nodes are just keys, right? So again, you should remember, if you are taking this type of keys, when you are studying the terms like keys, you should understand like the keys may be some values of attribute, right? Say for example, if I am dealing with this type of table, you should understand why this is not some random numbers. This value inside these nodes or these keys may be some attribute values of a table. It may be a register number, or it may be a date of birth, or it may be age, any other attribute which has the ability to act as a key, that we can use as a key. That's what we are studying as key. This is not random numbers, right? It may be of any attribute values that has the eligibility to act as the keys. Fine. So then all data is stored at the leaf nodes. That's also fine. And all the leaf nodes are interconnected. That's good. Keys are used for directing a search to the proper leaf. That also we know, right? Then this also is a basic property. If a target key is less than a key in an internal node, then the pointer just its left is followed. If a target key is greater or equal to the key in the internal node, then the pointer to its right is followed. That is also we know about the characteristics of B plus tree. Now let us imagine, you can ask a question, sir, where it will actually works. Here we studied about B tree and B plus tree, where it will actually works, right? We may come across many such situations while executing this type of queries, right? Select star from student where department equal to CSE. This one we call it as equality search. And another thing, example of, please you can, I will correct this. This one is range search, right? This is an example for range search. I mistakenly typed as equality. So equality search, say for example, select star from student where department equal to CSE. This is an example for equality search. So based on this CSE, that checking or some retrieval will be followed. And again, this is for another range search. Please change. I will change the PPT. Now you also please understand. Example of range search. Select star from student where register number equal to our register number between the values. So again, I think it's Adarsh number, right? Adarsh, are you there? Adarsh?
Yes, sir. Yes, sir.
Yeah. Can you hear?
Here.
Right. And so this is this query is deployed to extract the data records between this register number 4001 and 4020. I think 4020 is Jyotika, right? Are you available? Jyotika? Fine. So that's all about example for a range search. So while using this type of queries, we should understand that the backend supported by this type of queries is nothing but the B tree as well as B plus tree indexing. Only the help of those proper mechanisms, it could able to provide that records in a fraction of seconds, right? That is the intelligent part we should understand about this B tree as well as B plus tree. Whenever you come across this type of queries, you should understand the concept of B tree as well as B plus tree. That makes the retrieval process much easier. Then the structure of a B plus tree. In the B plus tree, every leaf node is at equal distance from the root node. This is called leaf node, right? These all bottommost nodes, we call it as leaf nodes. These are all leaf nodes. Is of equal distance. Every leaf will be of equal distance from the root node. This is root node. Every leaves, this one set of leaves, another set of leaves. Every leaf node will be of equal distance from the root node. Then the B plus trees of the order n. This also we know. For a construction of a B tree or a B plus tree, we should maintain some order which will decide how much number of keys it can able to accommodate, right? Where n is a fixed for every B plus tree. Then it contains an internal node as well as leaf node. Here, as there is only the height is 1, we have only one. The same node will act as a root node as well as internal node, and this one we call it as leaf node, right? Then some basic requirements where an internal node of B plus tree can contain at least n by 2 record pointers. So what is mean by record pointers? This pointer we call it as record pointers, right? these pointers, that is besides each and every node, we call it as pointers. So this is one pointer, this is one pointer, this is one pointer, and another this is one pointer. So every nodes will have this type of pointers to direct to other searchings. Then at most an internal node of the tree contains n pointers. So if you consider a node here, internal node here, at most how much nodes, how much pointers it will have? 1, 2, 3, 4. So the size of the n, if the size of the n value is 4, then the pointers will also be 4 in numbers. Whereas the keys it can able to accommodate will be n minus 1. That we know already in B trees. We already studied in B tree. So if a value of B tree or the n value of a B tree is 4, it will have 4 pointers, right? And as well as the keys will be n minus 1. So it will having 3 places for accommodating the keys. Then the leaf node. So the leaf node of the B plus tree can contain at least n by 2 record pointers and n by 2 key values. Then again, at most a leaf node contains n record pointer and n minus 1 key values. That's what we already know, right? Then every leaf node of the B plus tree contains one block pointer P to point to next leaf node. So this is the pointer here. This is another beauty of B plus tree. Every leaf node has a connectivity with other nearby leaf nodes. That's why B plus tree can able to accommodate. They can able to work with both direct access as well as sequential access. This is the beauty of B plus tree. So every leaf node of the B plus tree contains one block pointer to point to the next leaf node. This is the block pointer that helps to point to the next leaf node, and this is another block pointer that helps to point out to the next leaf node, right? That is all about internal node and leaf node. Then let us understand how a searching is performed in a B plus tree. Suppose we have to search 55 in the below B plus tree structure. So consider this is the tree we already have. It means this is, so again, if you have the clear imagination about index, you can easily understand this concept. So say for example, from this index itself we can understand. So what is our requirement? Our requirement is to find out key with value 55. So in the index itself, in that first root node itself, it is possible to decide where this record will be actually located. So I can understand that this 55 will definitely comes in between 50 as well as 75. So I will skip all those searching here. I will directly move to this pointer 50, between this 50 and 75. From that 50, I can again know it will come to the right side of 50. So I will go to the right child and I can easily access this particular record of 55. That is the searching of what? Searching in the B plus tree. So first we will fetch for the intermediary node. We will direct to the leaf node that can contain a record for 55. So you can read the theory parts, right? This is the mechanism. So once there is a requirement of finding out the key, it will approach the root node. Based on the root node, it will decide from where this key will be actually located. From that, it will go to the left or leaf nodes in which the file or which the key is actually located. So now we can able to easily understand this will be found in the right side of this 50. This is one example for us searching in B plus tree. Then suppose you want to insert a record 60 in the below structure. See here you should understand this searching, insert, deletion, everything is very common, or you should be able to try to correlate with what in a normal physical records you used to perform insert operation, deletion operation, updation operation. That's what we are also dealing with here, right? I am interested in searching a particular record. We are giving us a key, but actually this key may be one such attribute value or a key value for a record. That's what we should have the understanding. This is not random numbers, right? This may be the attribute value or the attribute value which has the ability to behave as a key value, right? Then now I am going to insert a record with some value as 60. So again I will approach the root node. I understand that this should come, this is the range, right? This 60 comes between the range of 50 and 75. So again, after understood this first criteria, I will be moving to the rightmost child. As 60 is greater than this pivot element 50, I will move to the right side of this 50, or I will go to the right child. In that child, I will try to accommodate this 60. So again, we know when this node is getting filled, what will be the situation in a B tree? This, if the node is getting filled due to some insertion, that middle element will become the root node, or middle element will be promoted as the root node, right? That's what we the understanding we have already in the B tree. So now when 60 is trying to find its place in this node will get filled now, because the maximum capability of this node is 4, because the value of n is 4, right? So then now it's when it trying to, the n value is 5 here, so it can able to accommodate only 4 key values. So when this node is, when the keys is, when the 60 is trying to be inserted between this 55 and 65 this will overfill this node, and it will become the 60 will become the root node now. Now the next slide you can understand. Now the 60 has become the root node, because here when it is trying to occupy its place, it is filled, so it will virtually get its place here. Once it got its place, once it got the virtual place here, this 60 will become, as it is a middle element, the 60 will become will be promoted to the root node, and the remaining this 56, 55 and 65, 70 will become the children of this 60. That's what happened here. So now 60 become promoted to the root node, and other child becomes 50 and 55 will become the leftmost child, as it is less than 60, and 60, 65 and 70 will become the rightmost child. And again you may have a question, why we are having this 60 again here. So that is also one of the important beauty of B plus tree. Whenever a key got promoted as a root node, it will still retain its place in the child node for easy access, or for easy access of the records. It will maintain, it will retain its place in the node from where it has emerged as a root node. So see, you can also see here. So it means 50 in the earlier stage, 50 was promoted as a root node. So 50 will be retaining both in the root node as well as in the leaf node. And in another some situations, 25 has become the root node, and it also retained in its leaf nodes. That is the reason why we are having this 25, 50, 60, 75 in the leaf node as well, right? At some stage it has happened like 25 has been promoted as promoted as root node, but still it will maintain its state in the leaf node as well, right? Fine. Then again the deletion is also simple as a normal parameter. Suppose we want to delete 60 from the above example, the same will happen. If you want to delete this 60, what will happen? All these other, it will take its previous state, right? So again, if you deleted 60, then 50, 55, 65 and 70 will come to the leftmost side of this 75, the parent node 75, and the 75, 80 and 90 and 95 will become the rightmost child of this node. That's what we call it as what? This deletion, right? Now let us have another example, how to create or insert in B plus. Let's start from the beginning. We are constructing a B plus tree. It means here we have, these are some key values, right? If n equal to 4, then n is the order, then key will be n minus 1, that will be 3, right? So say for example, here we can able to accommodate 3 key elements. As the value of n is 4, n minus 1 key we can able to accommodate, right? So 2, 4 and 7 will be accommodated in the first round of insertion or creation, right? Then what will happen if you are trying to insert 10? Then 10 will try to find its place here after 7. So once, now what will the situation? Now this 4 will become the root node, as it is not possible because the value of n is 4 and it can able to accommodate only n minus 1 keys. Maximum it can able to accommodate only 3 keys. So once if 10 comes to find its place after this 7, automatically 4 will become the root. It will break this node and 4 will become the root followed by its own children. Let us see what happens. 10 is getting added. Now 4 become the root node followed by the partition. The leftmost side has 2 and again the 4 is retaining in its place. That's what we saw in the example. 4 will retain its place in the leaf as well, followed by this 7 and 10. Now the next element is 17. Where will be where the 17 will try to accommodate? It will go to the root. It will find, it will understand it should go to the rightmost child. Then again it will search to the rightmost child and it will find the place after 10. Now according to the property, again it is breaking the rule because it can able to accommodate only 4. So virtually it will add here. So what will happen? This 7 will become the root node. It will break the node and 7 will be promoted as the root node. So what will the situation will be? The 7 becomes the root node followed by 7, 10 and 17. And again, the another element is 21. Now what happens? This 21 approaches this root node. It understood that it comes in the range of this 10 to greater than 10. So it will directly go to the rightmost child of 10. It will find its place. Then it will store it after this 70. That is fine. And again, the last element is 28. What will happen? This 28 will again, it will come to the root node. It will understood that it should go to the rightmost child and it will try to virtually get the place after 21, but it is not possible according to the rules. So again, what will happen? This 28, this 20, the 17 will become root node. Again, if you are adding 28 here, the 17 will become root node and it will be followed like this. Again, if you are adding 17 here, what will happen? This root node is getting overfilled now. So this root node will be broken and this 7 will become the root now. So the situation will be like this. 7 will become the root followed by this 4 and 7, 10, 17 and other parameters, right? So this is the criteria of what? Creating a B plus tree. And the advantages of the B plus tree you can understand. We can access data stored in a B plus tree sequentially as well as directly. And keys are used for indexing. And faster search queries as the data is stored only on leaf node. So you can understand all these keys element will be stored only in the leaf node. So you can find all the records here. 2, 4, 7, 10, 17, 21, 28. Every records can be retrieved from the leaf node. That is the beauty of B plus tree. Right. So again, this is the advantages of this B plus tree. So again, you know something like this is the linked list. We call it as what? Linked list. We know the concept of linked list, right? This one, the leaf nodes will again, they will try to form a link to form a linked list. That's what we already know. This B plus tree is capable of supporting both dynamic as well as sequence success. It is possible to perform both dynamic as well as sequence success with the help of B plus tree. And this one we call it as what? A sibling pointer, right? This each and every connectivity between the leaf nodes, this one we call it as, you can note it down, this connecting point we call it as sibling pointers. Sibling pointers. This pointer, this is one sibling pointer, this is one sibling pointer, this is one sibling pointer. And the complete set of these keys we call it as sequence set. The complete sequence of these keys we call it as sequence set. Okay, these are the basic idea of what? B plus tree. So hope you have understanding about how the B plus tree is working. You should remember, again, you should remember this. Whenever you are coming across this query, you should remember that we are using what? B tree as well as B plus tree, right? And please change this one. This should be like range search. I typed as equality. It should be as range search. Example of range search. Example of so that's the example of range search. So whenever you are coming across this type of queries, you should remember the concept of B tree as well as B plus tree. Only with the, so you can understand here. So if you want to randomly, you are thinking like you have you want to access some lakhs of records, right? And you know only some few information about the records. It may be say imagine you have the table, students table. You have only some basic idea or attribute about his register number or date of birth, whatever it is. With that, if you are forming a proper indexing mechanism, it is much easier to make use of this type of query possible. So within a fraction of a second, you can able to get the query, right? You can get the answer. If you are typing this query and executing, how it is performing, it will form an index based on its interest. The B tree will try to find out mechanism to form an index. Based on that index only, it can able to quickly provide the results, right, without any type of delay. That's what the purpose of this B tree as well as B plus tree. Right, so you can expect these applications or questions in the exams also. So, right, shall we go for the queries? Queries? Anyone? Or you can post your comments now. Abhi Krishna, have you understood? Fine. So both this B tree as well as B plus tree will be of, we can expect this for the university also, right? And one of the interesting concepts, wherever you go, you should remember this type of concepts, B plus tree as well as B tree. Okay. You can attend the poll. You can get the questions from the poll. You can attend the poll, and after that we can stop the session. Any other queries? Meera? Any other? If there is no queries, you can type as no queries. If I want to summarize, I can summarize. Have you understood the concept of indexing as well as why we are using B tree and B plus tree?